Welcome to another video by Tiffany Zong from Physics 2011 section M6. This time round I'll be narrating Lab 5, the motion of falling objects. The purpose of this lab is to analyze the physics of various falling objects. Specifically, we looked at the forces of drag and gravity which act on the falling object to determine its velocity. In this lab, two different objects will be dropped to an equivalent height at the same time in order to compare the differences in drag force acting upon them. Because no initial force will be applied to the objects when they are dropped, the motion of the falling objects will be stalled by the downward force of gravity. Gravitational acceleration causes objects to increase in speed as they fall downward, but as the speeds of the objects increase, drag forces caused by air resistance also increase, slowing down the rate of acceleration of the objects. Because drag force is dependent upon velocity and acts in the direction opposite to gravity, a falling object theoretically reaches its highest possible velocity, or terminal velocity, at the point when the magnitude of the drag force becomes equivalent to the magnitude of gravity. Theoretically, when no drag force is present, objects dropped from rest at the same height will take the same amount of time to fall, regardless of factors such as their weight, shape, or material. However, because of drag forces, objects with different shapes fall at different speeds, and the masses of objects also affect their terminal velocity. For this comparison of drag, we dropped a pencil on a small piece of paper at rest from a height of about 2.5 meters above the ground. A video was taken of a smartphone camera and analyzed the tracker where we set a calibration stick to 15 centimeters in length based on the length of the pencil used in the procedure. The section of the video isolated for examination was 45 frames long and lasted about 1.5 seconds with a frame rate of 30 frames per second. Notably, however, the pencil fell faster than the piece of paper, so its motion lasted only for about 1 second. After tracking the motion of the objects using these parameters, the data was exported to Excel and graphed. Notably, the graph of the motion of the pencil is slightly more parabolic than the graph of the motion of the paper, which implies that the pencil had less drag forces acting on it because the greater magnitude of drag, the faster an object reaches terminal velocity and the slower its terminal velocity is. Furthermore, as we explored in the previous lab, an object moving at constant velocity has no net forces acting on it. Because the graph of the position versus time of the piece of paper appears mostly linear, we can assume that very little net force acted on it during the time it was falling. This analysis is consistent with the observation that the pencil fell at a faster rate than the piece of paper. However, in order to verify the effect of drag on the motion of the objects, we modeled drag forces for the different falling objects in PHYS using the approximation for drag. Force of drag is equal to negative b times the magnitude of the ball's velocity squared times the unit vector for the ball's velocity, where b is a constant to account for all the various factors that affect the drag acting on an object. Then, the drag force was added to the gravitational force to find the net force of the system, which was multiplied by the change in time at different time steps to find the change in velocity over time. The time step for the models was set to 0.033 seconds based on the frame rate of the observed video for comparison purposes, and the total times the motion was set to 1 second and 1.5 seconds to match the pencil and paper's observed motion times respectively. The models were then tested over and over again with different values of b until the final positions of the objects matched the final positions of their observed motion. Then for comparison, the second set of models was created with the drag force disabled. Data from both sets of models was output and then exported to Excel and graphed against the original data. In these graphs, the red dots represent the motion of the model data, while the blue dots represent the original data. As we can see, the models with drag roughly follow the path of the original falling objects, although the model for the motion of the pencil is more parabolic than the model for the original pencil. This difference may be at least partially accountable to errors in tracking the pencil's motion in the source video because the pencil is very difficult to see many frames of its motion. Regardless, the very small amount of drag used in the model for the pencil did allow the pencil in the model to travel the appropriate vertical distance in the appropriate time interval. The second set of graphs without the drag is very telling. The motion of the pencil in the graph without drag is very similar to that of it in the graph with drag, which makes sense because the drag of the pencil is bound to be very small. However, without the drag accounted for, the piece of paper in the model follows a much larger vertical distance for its time interval than it fell in the observed video, showing that drag definitely had a major impact in the motion of the falling piece of paper. Finally, we'll use some more models to consider a what-if scenario, where the objects are thrown with an initial velocity. When we set the initial velocity to 20 meters per second in the downward direction, the paper actually falls upward at first, presumably because the drag force is higher than the force of gravity, and then falls back downwards at terminal velocity. The pencil with initial velocity follows a mostly straight path, suggesting that it reaches terminal velocity much quicker when it has an initial velocity. But when the initial velocity is just put in the models without drag, the result is still just parabolic. In the end, we can conclude that because of drag forces, motion for falling objects varies depending upon the type of object that's falling. And that variation can be very significant, as we see of our observation with the pencil reaching the ground in less than 2/4 the time it took the piece of paper to travel the same distance. Furthermore, because the piece of paper's graph of motion was mostly linear, we can assume that it reached terminal velocity rather quickly, while the pencil does not appear to have reached terminal velocity in the interval it fell during. We can make the prediction that objects like pieces of paper which have a large area of contact with air compared to their weight tend to have higher drag and reach terminal velocity